Hello everyone. So today we are discussing visual defect detection. We are teaching computers to find cracks in concrete before they become a major problem. So because this is something like that, we can think of it as giving infrastructure its own medical checkup, but without all the paperwork. Coming now to a project overview. Manual inspection of infrastructure is incredibly tedious. Imagine staring at concrete all day looking for tiny cracks. Our project automates this process using a deep CNN that classifies images are cracked or non-cracked with impressive accuracy. The impact is significant. We're reducing inspection time by over 75%, allowing inspectors to focus on complex cases while ensuring consistent analysis. This matters because infrastructure safely affects all of us. When bridges, highways, or buildings develop undetected cracks, the consequences can range from costly repairs to potential disasters. Our system helps catch these issues early, making public spaces safer while saving money and resources. Getting over to our objectives. Our project has four main objectives. First is building an end-to-end pipeline for concrete crack detection that works efficiently from image input to classification output. Secondly, ensuring data integrity through a zero and clear organization. Because you can't analyze what you can't find, we have zero loss in this. Thirdly, conducting throughout exploratory data analysis to understand biases and patterns in our dataset, ensuring our model generalizes well to real-world conditions. Finally, deliverable actionable insights are delivered to us that maintains teams and can immediately use to prioritize repairs and allocate resources. By meeting these objectives, we're not just building a cool tech demo. We're creating a practical tool that immediately improves infrastructure and management while potentially saving lives. And that's something concrete we can all stand on.
Coming to dataset overview, let's take a look at the data powering our crack detection system. We are working with the SDNet 2018 dataset, an impressive collection of over 56 images capturing concrete surfaces across three categories: decks, walls, and pavements. Each pavement is labeled in one of two categories: cracked or non-cracked. Cracked images contain visible feature lines ranging from hairline cracks to more substantial features. Non-cracked images show impact surfaces without damage. What makes this dataset particularly valuable is its diversity. These image feature varying lightning conditions, textures, and crack severities. Preciously, the kind of variability we encounter in real-world inspections. Some cracks are obvious even to an untrained eye, while others are easily missed by human inspectors, especially after hours of repeated assessment. This realistic challenge is exactly what we need to develop a robust system. Unlike perfectly controlled laboratories images, these photos reflect the messy reality of field inspections, shadows, surface irregularities, stains, and all the other elements that make cracks detection challenging. Coming to data wrangling. Before we could train our model, we need to wrangle this data into shape, and this was no simple task. We started by flattening the dataset's zip structure into a more in, initiative hierarchy. Decks, walls, and pavements at the top level, each containing cracked and non-cracked subdirectories. Data integrity was paramount, so we implemented rigorous checks to remove duplicates and verify file integrity. This cleaning process ensures our model learns from unique, uncooperated examples rather than being biased by repeated images. For training, we created stratified splits: 70% of training, 50% for validation during development, and 50% for final testing. This satisfaction preserves class balance across all splits, ensuring our model sees representative distributions of surface types and crack patterns throughout development. We also built flexibility into our pipelines by supporting multiple files extensions, PNG, ZIP, and TIF formats. Accommodating this mixed format reality of infrastructure inspection data. This meticulous data preparation might seem tedious, but it's the foundation everything else depends on. By establishing clean, well-organized data from the start, we have saved countless hours of debugging and eliminated potential sources of bias that could undermine our model's real-world performance.
Moving on to exploratory data analysis. When we started looking at the images, one of the first thing we noticed is that crack comes in a lot of different forms. Some of them are really obvious, like deep fractures that you can spot instantly. But a lot of cracks are actually very fine, like teeny hairline cracks, and these are much harder to detect even by eye. Also, there's a lot of variation in lighting. Some images are bright and clear, but others are taken in a shadowy conditions, making these cracks even harder to see. Another challenge we found is even non-cracked surfaces sometimes have rough textures, like bumpy pavements or old walls, and visually these patches could easily confuse this model into thinking there's a crack when there is no crack. So overall, EDA showed us the dataset is very realistic, but it is complicated, and it's not clean, perfect dataset where even every crack is obvious. So that's why data augmentation became super important for us. We decided to use techniques like random flips, random brightness adjustment, and maybe even some slight rotations to teach model that cracks can appear in any orientation or under different lighting conditions. If we had skipped this step, the model would probably performing well only on very clean, easy images and fail badly on real world examples. So coming to model architecture, once we understood the challenges of EDA, we wanted a model that's not too heavy but still powerful enough to catch the very subtle features like small cracks. So first we resized all images to 128 by 128 pixels, and this size was kind of sweet spot, small enough to train faster but large enough that small cracks are still visible. Then we built a series of convolution layers. Each convolution layer applies a set of filters to the input image, basically detecting patterns like edges, corners, and textures, all the small details that help identify cracks. So after each convolution, we added a ReLU activation function. Here, ReLU helps introduce nonlinearity into the model, which basically means model can learn in more complex relationships instead of just simple straight line patterns. So we also added max pooling layers after convolution, which downsample the feature maps. And also pooling helps in two ways. It reduces the size of the data and making computation faster. And it also focuses on the model uh, on the most important features. After a few layers of convolution and pooling, we flattened the output and connected into a dense layers for the final classification, cracked or non-cracked. We also added dropout layers in between, and here dropout layer randomly turns off a new neurons during training, which forces the model to not rely too heavily on any one feature, and this really helps preventing overfitting, especially because our dataset has so many variations. For optimization, we use Adam optimizer with learning rate of 1 exponential minus 4. Adam works well because it adapts the learning rate automatically and speeds up convergence. And one final trick we used was mixed precision training. This uses lower precision wherever possible without losing accuracy, which made our training on GPU much faster. So overall, the architecture we built was simple but effective. It's able to pick up both large obvious cracks and small hairline fractures under different conditions. So, and with this model setup, we are ready to move to training phase, which Janavi will explain next.
Well, in the training pipeline, we have trained our crack detection system where we resized the images and we took a batches of 64 to keep both the training fast and accurate. And then we have, as already mentioned in the model architecture, that we had used the data augmentation for making our model smarter in the Adam optimization during the training period. Now, this is what we have done in the training pipeline. And next, coming to the performance matrix, our model gave us an 87% accuracy on the training set and 84% on the test set. This small difference shows this actually learn the patterns well, not just memorizing the training examples. While we have got a high accuracy and ROC AUC score of 0.92, and we have an well precision and recall was around 85, which means we are good at finding the cracks without too many false alarms. So bottom line of the performance matrix was the numbers mean faster, more reliable inspections and catching the problems earlier before they become the big issues. Now coming to the confusion matrix, the confusion matrix shows us the real world results. Like The 14% of cracks were missed, which are false negatives. This is not ideal, but much better than humans inspection, especially when people get tired. 18% were false alarms, like false positives, which just means a little extra checking. Better safe than sorry. Depending upon the situation, we can adjust the system to catch even more cracks if needed. So, from the confusion matrix conclusion, I could tell our system can change how infrastructure maintenance is done, helping teams to inspect more plays faster while human effort for the most important cases. Now, Mani would
Recover and
end.
AUC. This rosy plot shows the trade-off between true positive rate and false positive rate across thresholds. The curves paid this the curve very a rapid ascent towards the top left corner reflects strong discrimination with an AS of 0.8 with a AS of 0.85. This model achieves excellent class separation. We evaluated F1 scores across various thresholds and found that the standard zero point 0.5 cutoff yields the best balance of precision and recall, making it a reliable default in production. Coming to sample misclassifications, we here are 9 representative error cases. You can see here. Many false negatives involves hairline cracks that blend into texture backgrounds or appear in shadow. False positive often arise from through surface that mimic crack morphology. These examples highlight two main failures models: low contact cracks and texture confusion, which we can address through specialized data augmentation. Coming to the conclusion, to conclude, our transfer learning pipeline delivers 84% test accuracy and 0.92 AUC, automating over 75% of manual crack detection effort. This model is robust across decks, walls, and pavements, but struggles with low contact and shadowed cracks. Rigorous EDA guided our augmentation strategy and the end-to-end workflow. From data wrangling into analysis, ensures reproducibility and clarity for stakeholders. Looking ahead, we plan to extend this work by transitioning to segmentation for precise crack localization, enriching the data with diverse lighting and material conditions, integrating classical edge detection as auxiliary inputs to improve sensitivity, packaging the model into a mobile or web app for field inspections, connecting results to enterprise assets management systems for automated maintenance scheduling. Here you can find the references like we took the SDNet 2018 dataset and the TensorFlow documentation that underpins our implementation. Thank you.